kind of video, I want to do a post preview for you. I'm going to have the links to this video in the description below. Now, you might have heard NASA announced last week there is a new asteroid on its list of potential asteroids that might hit the Earth. This one in 2032. They give it a 2.4% chance. And I thought we'd look at that probability, not just for that asteroid, but for all such large rocks that they track. This is a picture of past impact craters, which we'll get to in a moment. I'm just going to scroll through this post and leave you the main thoughts. And if you want details, you can go to the post and read this. Now, this one here, that it's going to come, it's a boring name. I think they call it 2024 YR4. And if it does hit, it's going to be something like a 7 point, it depends where exactly and so forth. But if it does hit, it would bring something like a 7.7 megaton blast. A 7.7 megaton blast is just a little bit smaller than our B-53 nuke, which they say has a megaton blast of about 9 megatons. The largest nuke is the Tsar Bomba, where they claim a 50 megaton energy capacity. I don't know how true these all are. But there was in 1908, you probably heard, the Tunguska event. And that has estimates from anywhere from 3 to 50 megatons. So this one that might hit in 2032 would be on par with that, or in the same ballpark anyway. What I want to get across here, I have this link here, you can read this, is it's not just the crushing, the crushing of the asteroid into the Earth, the impact and all that kind of stuff. It's the amazing heat that would be released as this thing plows through the atmosphere, building up friction and so forth. And there's a story, lots of stories of people who survived this. One guy was 40 miles away, and he felt like he was on fire, and there was fire damage in and around his village, 40 miles away. So if this thing does hit in 2032, it would be a big thing. Now, NASA has this thing called CNOS, the Center for Near-Earth Object Studies. And they track a bunch of things out for actually quite some number of years into the future, even hundreds of years into the future, the bigger objects. And I thought it would be fun to look at this database and record or calculate the probability of impacts by year. So we know that the probability of this one, according to their model, the conditional probability of that is 2.4%. But what about all the others? And what about all the other sizes and they track and so forth? And they have lots and lots of things that they do track. And they use a method of calculation that I'm going to only briefly mention in this video, but you can go to my the link in the description to look at this thing. To get the exact calculation, how to make it, and so forth. If you don't care about that, just skip over that and you can jump right to the pictures, which I'm going to do here. There is this paper, though, which I'll just briefly mention. It's the 2002 paper, Quantifying Risk from Posed by Potential Earth Impacts by Chesley and some others, and Icarus. And I'm not going to go into any of that except to look at this picture that they have here, if I can fit it all on one screen. This is an estimate based on previous work from others and looking at history and so forth, and looking at craters and all kinds of other evidence, observational evidence and so forth, looking at past impacts and overlaying some kind of a model over the top of these and to see how well they fit. And it fits really well. This is a log scale, log 10 to log 10 scale. This is the impact frequency. So 10 to the 1 means about 10 times a year we get an impact energy collision with some sort of rock from space, about 10 times a year, about 1 kiloton, or 10 to the minus 3 megatons. 1 kiloton, that's a lot. That's 1,000 tons of TNT, and of course a ton is 2,000 pounds. So that's quite a lot of TNT that hits into the atmosphere. Most of these, just make sparks and things like this, but a few slightly larger ones occasionally make the news and so forth. And you can see way out on the end here, there's 10 to the 8th megatons, which is which is responsible for, there's two of them that we have tracked out that far. One hit 65 million years ago or so and wiped out the dinosaurs, and another one hit about 2 billion years ago. So these things are rare, and they occur on average about 10 to the 8th years. That's every 100 million years. About every 100 million years, one of these monster rocks hits. And so we'll talk about that just a little bit below. So here's the data. Just as the CNOS data right here. Here is just of all the asteroids that they track, or rocks, or near Earth objects and so forth. Here's the estimated diameter of these things. And it's crucial that they don't know all of. If you read that one paper I mentioned above, they can have the reflectivity and so forth, and some orbital characteristics of these things. But the mass is not exactly known. The density of each rock is not exactly known. All of this stuff is estimated, which is why all this stuff goes in models, and which is why there's only probabilities attached to these things, because not everything is known about every particular object up there. Notice the log scale here. This is anywhere from 0.001 kilometers, or in other words, 1 meter, all the way up to over a kilometer in diameter, a kilometer in diameter. The smallest one they track is 0.053 kilometers. The 2032 object that we might get is about 0.53 kilometers, 0.053 kilometers, which is about 180 feet in diameter. And that's a pretty big rock to hit. Again, that would bring 7.7 megatons of energy to the atmosphere and the Earth. The biggest that they're tracking out here on the far right, on this far right out here, is about 1.3 kilometers in diameter, which is 4,200 feet in diameter. And that's not scheduled to hit until about 2880, which is obviously quite a number of years from now. None of us will be around to see it. And it has this thing called a cumulative probability of hitting of 0.00039. Well, I'll explain this cumulative probability below. It if it hits, would bring 75 billion tons of TNT, 180 megatons, which is roughly 75 billion tons. That's on the order of the asteroids. It's not quite as big as that, but it's nearing that ballpark of the asteroids that wiped out the dinosaurs and so forth. That would be a very large thing. The smallest object here is just over 3 feet in diameter, which is about the size of an average journalist. And it has a cumulative probability of 0.00088. I'm going to explain that cumulative. Its energy would be about 73 tons of TNT. Probably wouldn't make it to the ground, but it would, if you're under it, it would be interesting to see. Now, they have a number of tracked objects. I plotted the objects the first year of which it might potentially hit. A lot of these objects might hit more than once. They might hit more than once in a year, depending on the particularities of their orbits and so forth. But some of them might hit only once a year, or once every 10 years, or once every 100 years, or whatever the span of their orbit happens to be. So there's a kind of a U-shaped signal to this, but I think it's an observational and modeling artifact. The ones that are in real close, they have the best information on. The ones that are going to hit this year, for instance, or may hit this year, they have the best observations on, so they can quantify pretty exactly what's going on. The ones that are farthest out in time, there's not that many of them. They're the bigger ones and so forth, and they can get their orbits better. It's the ones in the middle that there's the greatest uncertainty. So I think that this U-shape here, inverted U-shape, is just an observational artifact. But there's lots and lots of objects. And in fact, here it is right here. Here, again, is the impact probability. The individual impact probability is calculated by NASA for each of the objects that they have. I think it's like 48,000 in the database. It's not 48,000 separate objects, 48,000 potential impacts. Some objects, again, might hit more than once. This probability here is at 0.24. And this is a log scale. This is 1e minus 2, which means 10 to the minus 2, or 0.01. So this one that sticks up a little bit above that is the 2%er. There's a big one out here I'll talk about in a second. But most of these average, this is 10 to the minus 8. This is 10 to the minus 5. It's 10 to the minus 8, 0.000000001. Pretty rare. But the average is about 1 in a million. The average probability is about 1 in a million. And I'm only showing out to the next century. I didn't go all the way out to 2880 and so forth. I've just looked at the next century. All right, so they have this thing called cumulative probabilities, and I'm not going to talk about that. It's a reasonable approximation to the probability. What they do is they calculate the probability of every potential impact for an object, and they sum those probabilities up, which answers the question, it'll hit at this time, or the next time, or the time after that, or the time after that, and so forth. It's answering the probability that it'll hit at any time. And the number of times that they think it might hit. That's only an approximation. There's a better way to get the exact probabilities, but when you're talking about probabilities down around 1 in a millions and so forth, their approximation is just dandy, and I have all the details. You can go and look at the papers. Okay, all the tracked objects, there's 40, it's not tracked objects, it's 41,848 potential impacts. And I wanted to calculate for 2025, what's the probability object 1 hits, or object 2, or object 3, or however many that there are available to hit in 2025. And then I want to look at 2026. What's the probability of object 1 that might hit then, or object 2, or object 3, and so forth. So I want the probabilities of any object hitting per year. And I get this picture here. And again, note the log scale here. This is 1 e to the minus 1, which means 0.1 or 10%. Here is 1% again, and 1 in 1,000, 1 in 10,000, 1 in 100,000, so on down the scale. Here, right here in 2032 is the 2.4%er. And you can see here, these are the average probability between now and a century out from now is about 1 in 1,000. Any year, there's a probability about 0.001 or 1 in 1,000 that something hits us of any size of the objects that they're tracking. I don't know if you think that's small or big, depends. But you know, if you're in the path of I have links to the path of the 2032 object, basically anywhere from just in the Central America, basically all the way through across the oceans, starting in India. So this can hit a lot of big population areas if we let it get that far. All right, now here is the second probability. It's the cumulative probability. So from our perspective, from 2025, what's the probability any object hits in 2025? And then the probability any object hits in 2025 or 2026. And then for 2027, the probability that it hits in 2025 or 2026 or 2027, and so forth, from our perspective now in 2025. And here is 1 e to the 00, which means 1. So once we get up to this level up here, that's a probability of 1. It's certain, according to NASA. This big jump right here that we see is from that object in 2032. That accounts for the most of this stuff. And this is the 0.5 line. So that's 50-50. This creeps up and up and up. And by the time we reach 2125, it's around 28% chance. In other words, there's a 28% chance in the next century we'll get hit by one of these objects. So I think that's very interesting. Of course, if they go out and there's things that can be done, perhaps to deflect the orbit of this 2032 object, maybe, or don't forget, there are objects up there that nobody knows about, and of course are untracked, so we don't have probabilities for those because we don't know about them. Now, we could do the whole thing. I did all of that for all the possible objects of all sizes and so forth. Here is doing the first figure again, but only looking at objects which will deliver 1 megaton or bigger. In other words, about the size of a nuclear weapon. Well, there's nuclear weapons, small tactical nuclear warheads that are on the order of, I think, 0.01 megatons. but these are on the order of 1 megaton or larger. And the probability here is still around 1 in 1,000, growing. It mostly grows in that middle area where there's more uncertainty and so forth, but it's still a substantial probability. Any year, there's about a 1 in 1,000 chance, anywhere from 1 in 10,000 to 1 in 1,000 chance that an enormous object will hit us and cause some kind of havoc. That will certainly be visible if you're under it or anywhere near it. I have links to all the data. The European Space Agency has tracked past impactors and so forth. The last one that hit was just a few years ago, was 4.46 kilotons. That's the biggest they have. That's somewhat large. I have details on all this, and you can go and look all this kind of stuff. That's it. That's the probability. All the detailed calculations are there, and I'm going to give you the link in the description below. And if you like these kind of videos, I can do them either in more detail or less detail, or just point to the post. You let me know in comments. Thanks very much for listening.